This lecture video is about conservative vector fields. So to start, here's the definition of a conservative vector field. So we say that a vector field F is conservative if it is the gradient of a scalar field. That is, if we can find a scalar field phi such that its gradient is equal to the vector field F, then we say that F is conservative. So in this case, the scalar field phi is called a potential function for the vector field F. Okay, so let's consider the following example. So here we have a vector field F in 3 dimensions. So we have 3 components for F, the X, Y, and Z. So let's take, for example, a scalar field phi in 3 variables, which is equal to 1/2 of x squared plus y squared plus z squared. So let's see if this vector field is conservative. Okay, to see that, let's consider the partial derivatives of phi. So note that the partial derivatives of phi are as follows. So phi sub x equals 1/2 times 2 times x, or x. Okay, so similarly, we have phi sub y equals y and phi sub z equals z. So these are the partial derivatives of phi with respect to x, y, and z respectively. Note that the results are precisely the components of the given vector field F. And so we say that phi is a potential function for F and that the given vector field F is conservative. So we have seen that the gradient of our scalar field phi is equal to the components of the vector field F. Okay, so later I will show how to compute or how to obtain this scalar field if F is conservative. Okay, so next, so here we want to show that the given vector field F in 2 dimension, negative y comma x, is not conservative. So to show that the given vector field is not conservative, let us suppose otherwise. That is, suppose F is conservative. So if F is conservative, then we can find a scalar field phi such that its gradient is equal to the vector field F. So given this, we have the following equations. Okay, so if the gradient of phi equals F, then phi sub x, or the partial derivative of phi with respect to x, must be equal to the first component of the given vector field, which is negative y. So similarly, phi sub y, which is the partial derivative of phi with respect to y, must be equal to the second component of f, which is, in our example, equal to x. Okay, so we want to solve for phi. We're given here the partial derivatives with respect to x and y. So to find phi, we integrate with respect to x or with respect to y. So let's consider first this equation, phi sub x equals negative y. So here we treat y as a constant and let's integrate with respect to x. So we have phi, which is a function of x and y, equal to, okay, so if we consider this equation, we have phi sub x, okay, and then integrate this with respect to x. Okay, since phi sub x equals negative y, then we have the integral of negative y dx. Solving for the integral, we get negative xy plus some constant c, where the constant c is a function of y. So note that if we have c of y, then its derivative with respect to x must be equal to 0, since c is only a function of y and is treated as a constant. Okay, so we now have an expression for phi of xy. However, we still have to know the expression for c of y. Okay, so let's go back to equation 1. Here we have phi sub y equals x. Okay? And we have here phi of xy. So here, let's differentiate phi of xy with respect to y. And so we have phi sub y equals derivative of this expression. Okay, we get negative x plus c prime of y. Okay, so we now have two expressions for, okay, we now have two expressions for phi sub y. So here we have phi sub y equals x and phi sub y equals negative x plus c prime of y. So we can equate these two expressions, okay, as we can see in the next slide. Okay, so we have these two expressions for phi sub y. So we have x equals negative x plus c prime of y, or c prime of y equals 2x. Now, what can you say about this equation? So note that the left-hand side is a function of y, whereas the right-hand side is a function of x. And so we get a contradiction since, again, c is a function of y only, so its derivative should be independent of x. Okay, so we got a contradiction for our assumption that f is conservative. Okay. Therefore, we have shown that f is not conservative. Okay, in this example, we want to show that this vector field into space is conservative. So to show that this vector field is conservative, then we must find a potential function whose gradient is equal to this vector field. Okay, so to start the solution, let's assume that a potential function phi for f exists. That is, the gradient of phi must be equal to the vector field f as follows. Okay, or in other words, the partial derivative of phi with respect to x must be equal to the first component of the vector field f, which is the exponential of 2y plus minus 2x plus 1. Similarly, we have phi sub y, or the partial derivative of phi with respect to y, equal to the second component of the given vector field f, which is 2x exponential of 2y plus 3y squared minus 2. Okay, so we now have expressions for the partial derivatives of the function phi. Okay, so to solve for phi of xy, let's consider this equation, phi sub x equals this, and integrate this with respect to x as follows. Okay, so we can obtain phi of xy from phi sub x by integrating phi sub x with respect to x. So doing this integration, we will get x times exponential of 2y minus x squared plus x plus some function of y. So again, c is a function of y, so if we differentiate this with respect to x, we will get 0. Okay, so from here, let's take its derivative with respect to y as follows. Okay? So phi sub y equals, so partial derivative of this expression with respect to y. So we will get 2 times x exponential of 2y, and then minus 0 plus c prime of y. So as you can see, we now have two expressions for phi sub y. Okay. So equating these two expressions for phi sub y, we get the following result. Okay. So notice that we have the term 2x exponential of 2y on both sides of the equation. So we can cancel that out. And so we are left with c prime of y equals 3y squared minus 2. So the left-hand side is a function of y, the right-hand side is also a function of y, so we can do the integration as follows. Okay, so from c prime of y, we can get c of y, which is equal to the integral of 3y squared minus 2 dy. So we get y cubed minus 2y plus some constant k. And so going back to the expression for phi of xy, we have x exponential of 2y minus x squared plus x plus c of y, where c of y is equal to this expression. Okay, so finally we have phi of xy equals this expression plus c of y, which is y cubed minus 2y plus k. And so we say that phi is a potential function for f and that therefore f is conservative. Okay, so notice that in this result, the potential function phi for f is not unique since we have this constant k in the last term of this function. So that's why we use the term phi is a potential function for f and not phi is the potential function for f. So we will see this in the next theorem. Okay. So this theorem is about the potential functions for a conservative vector field f. So this theorem states that if f is a conservative vector field and that phi and psi are potential functions for f, then phi equals psi plus k for some constant k. Or in other words, phi and psi are equal up to some constant k. Okay, so the proof is as follows. So let's consider the vector field f in R2 only. Okay. So now we have phi and psi are potential functions for f, then their gradient must be equal to the vector field f. Okay, and from this equation, we say that the partial derivatives with respect to x of phi and psi must be equal, okay, which is in fact the first component of f. Okay. Then phi sub x minus psi sub x equals 0, which means that phi minus psi is constant with respect to x. Okay, so in symbols, we have phi minus psi equals some constant with respect to x. Since phi and y are functions of x and y, and phi minus psi is constant with respect to x, then we have c as a function of the variable y. Okay, so given this, we know that the partial derivatives with respect to y are as follows. Okay, so phi sub y minus psi sub y equals c prime of y. However, from equation 7, since their gradients are equal, then phi sub y must be equal to psi sub y. And so, going back to this equation, okay, this one, since phi y equals psi y, then this must be equal to 0. Okay. So we have c prime of y equals 0, or okay. So the derivative is 0, so c of y must be constant. Okay. Or we say that c of y equals some constant k. So this expression completes the proof of this theorem. So we have shown that, okay, so from here, okay, equation 8, okay, phi minus psi equals k, or phi equals psi plus k. The previous theorem tells us that the potential functions for f are not unique. So in this example, let's verify that the given vector field is conservative by finding all of its potential functions. Okay, so to do that, let's assume that phi is a potential function for the given vector field f. That is, gradient of phi equals f, or phi sub x equals the first component of f, which is 2xy plus 1. Phi sub y equals the second component, which is x squared plus 2yz. And phi sub z equals the third component of f, which is y squared minus 2. So here we have expressions for the partial derivatives of phi. Let's now compute or solve for the potential function phi. Okay, so let's start with phi sub x. To obtain phi, we integrate phi sub x with respect to x as follows. Okay, so doing so, we treat y and z as constants. Okay, so we have the integral of phi sub x, which is 2xy plus 1 dx. Okay, so doing the integration, we get x squared y plus x plus some constant, which is a function of y and z. Okay, so again, here we treated y and z as constants, so c of yz is a constant in this case. Now let's compute for phi sub y by taking the partial derivative of what we obtained, okay, with respect to y. Okay, and so we have phi sub y equals x squared plus 0 plus, okay, so we have this notation c sub y because c is a function of two variables y and z. Okay, so again, we have obtained two expressions for phi sub y. Okay, one is x squared plus 2yz, and the other one is x squared plus c sub y of yz. Okay, so equating these two expressions for phi sub y, we will get c sub y of yz equals, okay, so as you can notice, we can cancel out x squared, okay, when we equate the two expressions. So we are left with c sub y equals 2yz. Okay, and we can now plug this in this, okay, in this part of equation 11. Okay, so from our results, we have phi sub y equals 2yz. Okay, so let's now go to the next slide. Okay, so we have c sub y equals 2yz. So solving for c by integrating this expression with respect to y, we get y squared z plus some function of z. Okay, so let's check. If we differentiate this with respect to y, we will get 2yz plus 0. Okay, so we can now plug this in the previous equation. So we have phi of xyz equals x squared y plus x plus c of yz, which is y squared z plus d of z. Okay, so one more differentiation and integration. Okay, so this is a function of phi. This is a function of x, y, and z. So we now differentiate with respect to z, which gives us 0 plus 0 plus y squared plus d prime of z, or y squared plus d prime of z. So going back to the previous slide, we have phi sub z equals y squared minus 2. Okay, and here we have y squared plus d prime of z. So equating these two expressions for phi sub z, we get Okay, so we can cancel out y squared. Okay, so we have d prime of z equals -2. Okay, so we can integrate with respect to z. So we get d of z equals -2z plus some constant k. And so from our results, we have, okay, from here, okay, and here, okay, we have phi of xyz equals x squared y plus x plus y squared z plus the expression for d of z, which is -2z plus k. And so these are all the potential functions for the vector field F. Okay, so let's now talk about the divergence of curl of the vector field F. Okay, so this theorem states that we have three scalar fields on R3. So they are P, Q, and R, and they are continuous. They have continuous first order partial derivatives. Okay. Now let the vector field F have the following components: P, Q, R, or the scalar fields P, Q, R are the components of F. So if these scalar fields P, Q, and R have continuous second order partial derivatives, then the divergence of the curl of F is equal to 0. Okay. So again, in this theorem, this states that the given vector field F has on for its components the scalar fields P, Q, and R with the following properties. Okay. The first order partial derivatives are continuous. Okay. And if P, Q, and R have continuous second order partial derivatives, then the divergence of the curl is equal to 0. Okay, so the proof is as follows. Recall Clairaut's theorem. So this theorem states that if the second order partial derivatives, okay, of a function are continuous on a domain, then its mixed partial derivatives are equal in the given domain. Okay. And so we have the following expressions. Okay. So the mixed order partial derivatives are equal in the domain since, again, the assumption in the theorem is that P, Q, and R have continuous first order partial derivatives. Okay, so given this, let's now solve for the curl of the vector field F. Okay, so the curl of F is equal to the vector, okay, R sub y minus QZ in the first component, PZ minus RX in the second component, and QX minus PY in the third component. So solving for its divergence, we will get RYX minus QZX, okay? So partial derivative of this with respect to x plus the partial derivatives of the second term or second component with respect to y. Okay? So we have this plus the partial derivative of the third component with respect to z, or qxz minus pyz. Okay, so rearranging the terms, notice that we have here, okay, let me choose this color, ryx minus rxy, which is equal to 0 from this equation. Okay. Also, we have q sub xz minus q sub zx, okay, which is also equal to 0 since they are equal. And lastly, we have p sub zy minus p sub yz equal to 0 since pyz equals pzy. Okay. And so the divergence of the curl of the vector field F is equal to 0. Okay. So this ends the proof for this theorem. Okay, so let's now talk about simply connected regions, where we can define such regions through the use of the following terms involving a plane curve C. So here, the plane curve C is parameterized by the vector valued function r of t, where t is from A to B. Okay, so we say that the curve C is simple if it doesn't intersect itself, okay, except possibly at the endpoints. Also, we say that C is closed if R of A equals R of B. So in other words, the initial and terminal points of the plane curve C coincide. So an example is a circle. Okay? In a circle, the initial and terminal points coincide, so the circle is closed. Okay? So a circle is also simple since it doesn't intersect itself, okay, except at the endpoints. Okay, so we can see more visualizations for these terms in the next slide. But first, let's consider the following definitions for a region D in R2 or R3. So first, we have the term connected. We say that the region D is connected if for any 2 points, say P1 and P2 in the region D, there exists a continuous path from the point P1 to point P2, which lies entirely in the region. Okay, and so finally, for the definition of a simply connected region, okay, we have this bullet number 2. Okay, a connected region D is said to be simply connected if every simple closed curve in D encloses only points that are in D. Okay, so to see these terms clearly, let's go to the next slide. Let's now take a look at the following parametric curves that are described using the terms that we learned in the previous slide. Okay, so this curve is not simple and not closed. So not simple because it intersects itself once, okay, at this point. Okay, and not closed because its initial point does not coincide with its terminal point. Okay, now let's consider the next parametric curve, this one. So this parametric curve is not simple and closed. Okay, not simple because it intersects itself, and closed because its initial point and terminal point coincide. Okay, now let's go to the figure on the lower left. Okay, so this curve is simple and not closed. Okay? It does not intersect itself, and the endpoints do not intersect or do not coincide. Okay? And for the last figure, okay, this parametric curve is said to be simple and closed because it does not intersect itself, okay, except at the endpoints. Okay, so from parametric curves, let's now go to the region D. So let's call this region D. So the shaded region corresponds to the points inside the region D, whereas the points inside these holes are not in the region D. Okay. So this region is not simply connected because recall that for a region to be simply connected, every simple closed curve in this region must enclose only points that are in D. So we can take, for example, this portion of the region. Okay. Okay. So we have found a simple closed curve that is inside D, that is inside the region D, but it encloses points that are not in D. So this region is not simply connected. And lastly, this is a visualization. Okay, so this figure is a visualization for a simply connected region. We can now use the notion of a simply connected region in the following theorem that gives us sufficient conditions for a vector field F to be conservative. Okay, so in this theorem, the vector field F is on R3 and is defined on a simply connected region and whose component functions have continuous first-order partial derivatives. So given these conditions for the vector field F on R3, we say that F is conservative if and only if its curl is equal to the zero vector. So note that this is a two-way statement. Okay? So we say that F is conservative if its curl is zero. Okay? On the other hand, if the curl is zero, then F is conservative. Okay? Now this gives us sufficient conditions for F in R3 to be conservative. How about vector fields on R2? So the conditions are given in the following corollary. Now in this corollary, we have two scalar fields, P and Q, okay, that are defined in a simply connected region in R2, okay, and that P and Q are scalar fields having continuous first-order partial derivatives. Okay, now suppose that F has the following form, that is, in its first component, it has the scalar field P, and on its second component, it has the scalar field Q. Then we say that F is conservative if and only if the partial derivative of the second component with respect to x, or qx, is equal to the partial derivative of the first component of f with respect to y, or that is qx equals py. So in this example, we have vector fields that are on R2 and on R3, and we want to determine whether f is conservative or not. So in the previous slide, we learned the sufficient conditions for F to be conservative. Okay, so in this example, it suffices to show that the conditions of the previous theorem or corollary are. So in number 1, the vector field F is on R2, so its form is as follows. So the vector field F is the following vector with components, okay, the scalar field P in the first component and the scalar field Q in the second component. Okay? So from the corollary, it suffices to show that Qx equals Py for F to be conservative. Okay, so let's solve for Py and Qx. So Py equals the partial derivative of 2x plus y with respect to y, which is equal to 1, and Qx is equal to the partial derivative of 2x with respect to x, which is 2. Since they are not equal, then we say that f is not conservative. Okay, it's that easy. Okay, now in number 2, again, the vector field f is on R2, where sine y minus y sine x is the scalar field p. Okay, and x cosine y plus cosine x is the scalar field q. So let's see if qx equals py. So solving for py, we have cosine y minus sine x. Now for qx, we have cosine y minus sine x also. Okay. So here we have shown that py equals qx, and so f is conservative. Now note that the vector field F here is defined on the entire R2, which is simply connected. And so F is, as I've mentioned earlier, conservative. Now that we have shown that this vector field is conservative, then you can now verify as an exercise that the potential functions for F are as follows. In number 3, the vector field F is on R3, whose components are given as follows. So y squared z cubed, 2xy z cubed, and 3xy squared z squared. Okay, so since F is in R3, then from the theorem that we had earlier, it suffices to show that the curl of F is 0 for F to be conservative. Okay, so computing for the curl of this vector field, we have the following setup. Okay, and computing for the cross product of this expression, we get the following vector, which is equal to the 0 vector. Okay, now since the vector field F is defined on the entire R3, okay, which is simply connected, and since the curl of the vector field is equal to the 0 vector, then we say that, according to the theorem, we say that this vector field is conservative. Okay, so now that we've shown that this vector field is conservative, then as an exercise, you can verify that the potential functions for this vector field are the following. So phi of xyz equals xy squared z cubed plus some constant k. Okay, so this ends the discussion on conservative vector fields. Thank you.